Hello, and welcome to the 19th lecture in the Jabra Reinforcement Learning series. So today we're going to be talking about a new algorithm, or shall I say a modification to an existing one. So we're going to be talking about semi-gradient SARSA, which is going to be our on-policy prediction for the control problem. So you can think of this as more of a continuation of our previous lecture. So just to recap, in the previous lecture, we say that if we have let me first represent it here so that we can see what I'm talking about. So let's say we're given a state space here, and this state space is too large. So we say that typically our goal is to update the value of a given state. We want to find what is the value of this given state under some policy pi, and this was our prediction problem. But the issue is that when this state space itself is too large, the algorithms that we've been using so far, like our standard vanilla Q-learning, SARSA, Monte Carlo, and so on, might not work as well because of our state space, if we use our state space representation as it is. And that is because while we're traversing our states, there are some states we won't be able to see at all, or that we won't visit enough, that it becomes hard to actually update them properly. And for this, we say that we introduce the idea of function approximation, where instead of trying to find the value into policy pi of some given state, we instead find the approximate value of a given state, which is parameterized by some weights, which we denote by W here. So the idea now was that, the size of W would typically be much less than the size of S. So as we can see, the resolution of our state space would decrease. But if we minimize the error over all the states here, then we should have a good enough representation of our state space that we can learn with a smaller resolution than if we were trying to update our state space in its entirety. So the idea that we went through was that typically we would try to, let me use a different color here. So typically we would try to minimize, there's a bad one. Okay. Typically, we would try to minimize the error between the true value of the state, right, and the predicted value of the state. So this is the error that we typically try to minimize here. So this would be our true value, and this would be our predicted value. Right, so that's what we went through, and I'm not gonna go through the details themselves of if you really don't remember any of this, please just go to the previous lecture and it would all be clear, because we have a motivation. Actually, we have other tricks that we performed here to actually make this prediction more visible, but ultimately we say that when we are trying to update our value of W, we would update it by saying W is equals to W plus alpha times. So this is, let's say in the case of TD0, we would have our reward R plus gamma times the value of our future state, which we denote by S prime, right, minus the value of, this is S prime parameterized by W in this case, because this is what we have, minus the value of S comma W, right, times the gradient of S comma W over here. So the idea here was that we would be taking the gradient of this term, but not this term, and the reason is explained in the previous lecture, which is why we were calling this a semi-gradient method. But now in this lecture, we are no longer being given some policy pi in which we're trying to find the value of. In this lecture now, the problem that we have is the control problem, whereby we're trying to find the best actions to take in a particular state. And we saw that when we're dealing with such a problem, the best way to go about it is so we're given, let's say, some state, and we can take action A1, A2, A3, or A4, or there might be a lot more actions that we can take here. And so what we have is a situation whereby that, instead of updating just our value functions, we want to make use of our Q function, right? Because usually we have our Q function, which is parameterized by S, A, right? Which would be our true value. But then, since we're doing function approximation this time, our Q function is going to be represented by S, A, W, right? So we can extend this, let's say we're doing again TD0 or SARSA in this case. We can rewrite this formula in terms of action values as, so this extension should be natural to you if you've been following these lectures anyway. So this becomes W plus, W is being updated to W plus alpha times R plus gamma of Q. So in the case of SARSA, we would have S prime, A prime, W. So instead of estimating the V function here, we're estimating the value of our future state and action minus Q of S, A, W times the gradient of Q S, A, W, right, which is our semi-gradient here. So that's the idea that we're dealing with in this case, right? So we are trying to, we're just following the same formula here where we're trying to update our value function and just extending it to the Q function, particularly in the case of SARSA. Of course, in the case of Q-learning, you would know that here we're not actually going to be we'll just be taking the maximum over all actions of this function, but we'll get into that in a future lecture. So this is our updated Q function, and now we need to think about, so what does the algorithm for this look like? And actually, I'm going to give a rough outline of the things I'm going to talk about in this particular lecture. So maybe I might put timestamps for that. We'll see. So first of all, we're going to talk about the pseudocode for semi-gradient SARSA. That's the first thing we're going to do. And after that, we're going to introduce a method known as tile coding, which is just a way we can represent our states so that they are feasible and so that we can actually use them to solve a problem. So we're going to introduce the mountain car problem. So this is a problem whereby you have a car on So actually, let me not introduce it right now. I'll talk about this problem later because we're going to be solving this problem. So we will introduce the mountain car problem, And then we will solve the mountain car problem. So this problem is actually on OpenAI Gym, and that's the one we're going to be solving for, using a combination of tile coding and semi-gradient SARSA. So we're going to be using these two methods over here to solve this for this problem. So we're going to be using tile coding and semi-gradient SARSA to solve this problem. And of course, we're going to be writing a program for this. So we'll be doing this in Python programming. So that's the rough outline of the lecture of the things I'm going to go through. And so we're going to deal with the theory stuff first, get that out of the way, so that we're going to translate the pseudocode in this algorithm to solving this problem and see how this algorithm as a whole works. So I hope you stick around until the end of the lecture, where we'll be talking about all those things. So I'm gonna insert a new page for that. So now we're going to go through the semi-gradient SARSA algorithm. So let me just, okay, that's fine. Semi-gradient SARSA. So we're going to go through the pseudocode for this algorithm. So first of all, so this is just directly from Saturn's book. So our input would be our Q function, which we denote, which is just a combination of our state and action. And we initialize these other variables. So we initialize step size, which is represented by alpha. We initialize epsilon, because we typically will have an epsilon greedy policy. And we initialize our weights, which is just some real value vector. So the idea here is we're going to loop for each episode. Right, so we start an episode, we select our state and action, right? So this will be our initial state and action. And the idea now is we're going to take, and of course to decide on what the state and action is, we just use our Q function that we initialize arbitrarily with some arbitrary weights. So the idea here is that we take action A. So you'll see that this is very similar to our SARS algorithm. The only difference is that now how we're updating our W. So we observe R and we observe our S prime. And if S prime is terminal, so if we reach a terminal state, the idea here of what we want to do is we want to update W as being equal to W plus alpha times R, the reward we're getting at the terminal state, minus our estimated Q value function here, Qs, A, W, times the gradient of Qs, A, W, right? So that's the idea here, and after that we all go to next episode. Otherwise, if it's not a terminal state, we choose A prime as a function of Q S, so as a function of Q, which if you remember, this is just some epsilon greedy policy that we initialize. So we just choose A prime by using our Q function, right? And we update W. So think about the difference between how we're choosing A prime here and how we would choose it in the case of Q learning. That could also, just in case you forgot, that will tell you the difference between this SARSA algorithm, which is on policy, and Q learning, which is off policy. So we've got gamma by the estimated value of Q, S prime, comma A prime, comma W. But of course, in the case of Q learning, you know that here you'll be choosing maximum over all actions of Q of S, comma A, comma W. That's the difference here. But here we're just following epsilon greedy policy, which is why this is an on policy method. So that's just a refresher for you. And we have Q of S, comma A, comma W times the gradient of Q of S, comma A, comma W, right? And then we update our S to become S prime, we update our A to become our A prime. So this, in a nutshell, is the pseudocode for our semi-gradient SARSA algorithm. It's pretty straightforward. And we are going to implement this algorithm when we're solving our mountain car problem. But if we are going to follow this, the next thing we're going to introduce is the concept of tau coding. And after that, we'll talk about the mountain car problem. So let's do just that. We're going to start talking about the concept of tau coding, which is just our way of representing a continuous state space. So you can think of this as discretizing continuous state spaces at different intervals. So let's say we are given, let's say we are trying to represent a point in the two-dimensional space, and we discretize it as follows. So let's say, so this is our, we call this actually a tiling. Let me just make that. This entire grid is called a tiling. And this inner grid, let me use a different color for it. This inner grid here is called a tile, right? So let's say we're trying to represent this point here, right? So if we look at the indices, let's say 1, 2, 3, 4, and 1, 2, 3, 4, we say for this tiling, let's call this tiling T1, right? So for tiling T1, we can represent this point by using the coordinates 3, 3, right? Because that's where it is. And if we have another point within the same region, we represent it by the same coordinates. And if we have a different point, let's say over here, then maybe this one is represented by, okay, maybe that's not clear, but you get the idea here. So the idea behind tau coding is just taking these points and then we discretize this space, and the points that fit into this the same box essentially get the same index, right? So that's the first part of it. So we have this tiling, but we could have another different tiling that is, let's say, shifted in this position, right? We have another tiling that's shifted more to the right. So I can't show it clearly here, but hopefully when we look at the code for this, it will be much clearer. And in this tiling, these 2 points, so let's call this tiling, maybe, what color should I use for this to be clear? Okay, I didn't use green. So we have our green tiling here, which I want to call T2, right? Maybe if we're looking at T2, these 2 points might fall in different tiles, right? For T2, they might fall in different tiles because T2 is equals to T1 plus some step size alpha, right? So we can create as many tilings as we want to, with just like the distance between them being some parameter, some value alpha, which is the step size here. So we could have what? Let me actually. We could have multiple tilings, right? So what I'm saying here is that we could have multiple tilings. So for tiling T1, we see that the points here, the green point and the pink point, they all fall to the same box. But for tiling 2, this might be different, right? They might fall into the same box again, but for T2, they might actually fall into different indices and so on. So that's the idea behind tile coding. So I hope, like to recap again, it's just discretizing the space and adding some parameter alpha whereby we create multiple tilings, like continuously discretizing the state spaces. So it's not that complicated. But in case it still confuses you, we'll look at it from the tile coding software that's provided in Saturn's book. And we'll just try to make use of that because the goal here is not to focus too much on this like feature engineering practices or state space representation things, but we just want to focus on the algorithm itself to ensure that we can solve the problem with it. But yeah, let's move on to representing the mountain car problem. So we're going to now talk about the mountain car problem. And this is the problem that we're going to solve by using a combination of both tile coding to represent the state space and the semi-gradient SARSA algorithm, to solve for the control problem itself. So first of all, let me introduce the problem. So let's say we have essentially, let me draw it here. We have like a hill here or a mountain, and we have a car at the bottom of this mountain, and the car's goal is to reach the top here. So the idea now is that the car is trying to build up momentum in order to reach this goal. So if it continuously drive forward, it's going to hit the steep of this steep slope and then fall back down. So obviously the optimal move may be to move forward, move back, move forward, move back, move forward again until you reach your goal. And this is a situation where things have to get worse before they get better. So the algorithm itself needs to learn to take actions on that are far away from the goal in order to reach the goal. So you need to actually we actually saw a similar problem before in the earlier lectures, but I'm not going to dwell too much on that. But the idea is this. So we're given this problem whereby our goal is to make this car reach the top of the mountain, and we have its position here that's represented by P. And essentially what the car can do, so I'll describe the action space. Oh, sorry about that. So the action space is as follows. So we have the indices. We can take action 0, 1, or 2. Action 0 would be accelerate to the left, right? Action 1 would be do nothing. And action 2 would be accelerate to the right. So again, as you can imagine, the goal is for the car to build up momentum, but maybe accelerating to the left, then right, then left again, build some momentum, and then reach the top of the mountain. So given this, our state space is represented as follows. So the minimum value, let me just identify minimum and maximum values of different parts of our state. So we are from minus 1.2 to 0.6 as the car's position, right? And we have minus 0.07 and 0.07 as the car's velocity. So that's our state. So our state is a combination of position and velocity, essentially. So what position is the car in over here, and at what speed, velocity is it moving at? What speed or? So the idea now is we need to define the transition dynamics here, because like I said, the goal itself is if position is greater than 0.5. So if the position of the car is greater than 0.5, then it reached its goal, right? So that's what we are trying to make happen. Let me just use pause so that I don't think some probability. But just to be clear, okay, this is P, this is V. So if we have position being greater than 0.5, then we'll reach our goal. So that's essentially what the problem is here. And the transition dynamics, as you can imagine, so this part should be pretty, the first part should be pretty straightforward, where we say the position at time step t plus 1 will be the position at time step t, right, plus the velocity at time step t plus 1, right? And the way we would update the velocity at time step t plus 1 would be equal to some velocity t plus the action we would take minus 1 times some force minus the cosine 3 times the position at time step t times some gravity. So these are very like specific because we are assuming that the reason why the car would fall back down is because there's some gravity, right, that is acting on this. Like, so you don't need to focus too much on the like transition dynamics here, but I'm just like denoting them here in case you're interested. So the force value here is 0.001, and these are the values that are just used on OpenAI Gem for solving this problem, right? So yeah, that's pretty much it. That's the idea behind the mountain car problem. And next, we're going to work on actually solving the problem in Python. And like hopefully it will give us a better idea of like how we can implement or like our like pseudocode, how we can translate that into actual code, at least in terms of solving this problem. So we'll be using a combination of like, we'll translate our pseudocode into actual real code, and we'll use the tell coding software that's provided by the book to represent the features. And after that, we're going to solve this problem. So now that we've finished setting up the mountain car problem, we need to initialize a few things. So the first thing is that we'll say our position. We'll say our position can take values between, say, minus 0.6 and minus 0.4. So actually I should use this to represent that. And so, and our velocity is always initialized as 0. So that means we can represent our initial state as something like, let's say an example, an initial state is minus 0.5 and 0. That could be a good example initial state. And initial action can be something like 0, which means move to the left. And from there, we'll take a bunch of actions and so on until we resolve for this problem. But like we said before, we're not going to be using these features as is. So we are going to be, because these features are continuous, we're going to be creating a feature vector to represent our state space. Or in this case, since we're dealing with Q values, we can represent our state and action space using our feature vector. So the feature vector would be something called, say, x. So we're given x of s comma a, right? So x as a function of s comma a. And essentially what this does is it gives us, it allows us to make use of our tile coding to get the various like values that we can use to represent our features. But the thing here is when we're like representing this feature vector, okay, so we're going to have something like, let's say we want to create say 7 tilings or 5 tilings. So we have T1, we have T2, all the way until say T5, right? This will be the values of these vectors at the different points. So what that means, if you remember, like, I mean, we just talked about it, like our tiling here, for instance, for the orange point, the tiling is the point 33. This is the index after we discretize the space using the tiling T1. So using the tiling T1, we can get the indices for point orange, for point the pink point, and the yellow point. Using tile T2, we can also get these values, but they might look a bit different from what we see here. So I am going to show you, of course, like the tile coding software that's provided in Saturn's book. And here they show you a simple example of like how the tiling itself is done, or how you can make use of the software. Of course, you can do this yourself. It's not hard to implement, but in this case, just to save time, we'll just make use of this as is. And you can just look through this if you're very interested in how it's being done. But I'm just going to show you a simple example. Let's see, there you go. So let's have a simple example. So let's say we want to create 5 tilings. So this is just creating a hash table with this many elements. So we want to create 5 tilings with points between say minus 0.5 position and 0 vector. And this is our first state, this is our second state, and this is our third state. Some of the states may not be possible in our example, but this should be fine. So let's run this. So we see that for our first, these 2 states are quite close to each other. So when we look at their feature vectors, they're very similar, right? Like they only differ by 1 element here, right? And this is the kind of like state representation that we want here. And we have this state that is actually much further than the first 2, and it's represented by an entirely different set of points. These points are essentially indices right now. So you can imagine that we can take these and maybe represent them by using some kind of, let's say, one-hot encoding. And based on this, we can actually define our like weight factor and find the value of QS, A. So to actually clarify this, as you can see here, now that you have an idea of how we can create our feature vector X using our tile coding, where we're just feeding this. Actually, we'd be feeding this and the action as well, as you'll see later on in our code, but the idea is the same. So for us to get the value of Q, S, A, W, this would actually be equal to W transpose X of S, A, right? So we're just transposing, or just multiplying this two, so this is just the sum between I0 up to D of Wi, Xi of S, A, right? That's essentially what this is. So we're just multiplying our feature vector after feeding it to our tile program with our weights. Initially, our weights are just some random numbers, and that's fine. Because eventually through training we're gonna reach our optimal points. So this should give you an idea of how we're going to find this values, but I just wanted to clarify that first. So let's actually go into coding our algorithm. So I've already taken the liberty of writing certain parts of the code, just so that we don't focus on things the unimportant bits of this code. And I'm just going to show you an example. So let's actually run a simple test for this. So we're using the gymnasium library, and we're creating our mountain car environment. And the bit we need to focus on here is the action. So we start in a random state. We take an action here. This is a random action. We're just sampling random action from our action space. And then we compute our next state reward by taking a step in the environment. So our algorithm is going to replace this part because this is our policy. That's the part where we're going to, based on our previous state, our previous action, and so on, we want to determine what's the best action to take. So for this, let's run this. So as you can see, this is the situation we're in. Right now we're taking random actions, which means we're not really doing so well. But hopefully after actually implementing our SARSA algorithm, we'll be able to have a mountain car that performs better than this. So for our algorithm, we've initialized some of the things. So I'm going to put this pseudocode nearby as well so that you can see. Because we've already gone through this, we need to initialize things like step size, alpha, epsilon, and the Q, and so on. So what I'm going to do is, this is alpha, right, which is our step size, epsilon, right, for our epsilon greedy policy, gamma, which is just our discounting factor. Number of tilings I'm using here is 7. So again, if you don't really understand how the tile coding is working inside, please just go to the page that I showed and it will be very clear. And then we're going to initialize our weights to be between minus 0.05 to 0.05. And this is just some things we need for the tile coding software. And so these are the functions that I defined for creating the feature vector using some one-hot encoding as well on top of that. But let's not focus on this. This is not the point of this lecture. So we want to focus on creating our training process, how we update the weights, and the Q function, right? So the Q function, we've already described what it is in this scenario. So we have said for the Q function, essentially what we do is we return the dot product between our weights self.w here that we defined, which is the random weight over here, and our feature vector, right? That's essentially how we that's essentially what our Q function is, Q of S, A, W. And then the next thing is we want to start the training process, right? So one of the inputs, of course, is going to be the environment itself, and we want to get the initial state of the environment. So to do that, we start like this, state, let's just use the same logic. So self.environment.reset, right? So that will give us our initial state, and then from this initial state, we're going to take an initial action. We're going to say action is equals to self. We have a function called select action, which is supposed to follow some epsilon greedy way of selecting the action, right? So now you might be thinking, okay, how are we going to be selecting action? So let's go to our select action function and actually write it. So select action has a state and it has a flag of whether we want to use epsilon greedy or not. This is just for during training. That's fine. We want to do that, but when we are doing our evaluation, we just want to take the best action, right? So for select action, what we're going to do is we're going to first define how many actions we have. So, sorry. I need to, yeah. So we define number of actions, which is self.environment.action. Self.environment.action space .n, right? This will give us the number of actions that we have in our action space, right? And we can list this up. We create, let's say, a list with these actions, which is just saying range number of actions. So if you remember, 0 is for left, accelerate to the left, 1 is do nothing, and 2 is accelerate to the right. We create an action value dict. So what this is, it will tell us the value of taking each action, right? So this will give us the value of taking each action. And then for action, we want to estimate the value of each action essentially. So we're going to iterate through each action. And what we're going to do is we're going to get our feature vector, right, which is equals to self.hash feature vector. So we're going to hash it with our state and our action. Right, we're going to take our feature vector, we'll hash it with our state and action. And then what we're going to have also is the Q value for this. And to find the Q value, as you would expect, we'll call the Q function that we defined before. And we're going to feed it with, so this feature vector actually just comes out as a list, so we just need to convert it to a NumPy array, right, for the feature vector. So after that, we can set action value dict for our action. So the value of our action is equal to the Q value that we just computed, right? And that's it. So now we have the action and the value of each action. So we want to implement an epsilon greedy policy here. So we need to define what our greedy action is. Right, what is our greedy action? Well, this is the action that gives us the maximum value, right? So we look at our action value dict. We try to see which action is going to give us the maximum value. So we're going to action value dict dot get. So this returns us the action that has the maximum value in the dictionary, essentially. So what we want to do is say, well, if we're doing inference here, say if not epsilon greedy, then we just return the greedy action, right? So let's actually try running this in our thingy here. Where is our train state? let's set epsilon greedy to false. And of course, I also have a train.py function here that just calls like SARSA with a certain number of episodes and then just trains. So that's what we'll be running. So I just run python train.py. Sorry about that. Where were we? Saying train. Yeah. Print action. Let's print action to make sure that this is actually working as we'd expect. So this is giving us the second action pretty much most of the time. But that has to do with our await initialization, and I'm using some seed, so that could be the case. So, but anyway, in this case, it is working just fine. So what we do here next is we now need to define our non-greedy actions, right? So let me undo this so that, where was it? Let me undo this. Okay, so now we need to define our non-greedy actions. So non-greedy actions. So to define our non-greedy actions, we are going to look at, say, the set, right, of, let's say, all our actions. So the set of, say, range. Actually, I've already defined that. The set of actions minus our greedy action. So we're looking at the set of actions minus the greedy action, and we're going to list this. So these are our non-greedy actions, right? Anything that's outside the actions that we took already. So the idea now is we need to define, so if we are following some of our previous programming lectures, all of this stuff should be pretty much straightforward. But if this is new to you, I'll just explain. We need the probability of taking the explorative action, right? Which is essentially equal to self.epsilon divided by the number of actions, right? And we need the probability of taking the greedy action. So the probability of taking the greedy action, which is essentially 1 minus self.epsilon. This is from our earlier dynamic programming lectures, plus the probability of taking explorative action, right? So the action itself that we end up taking using an epsilon greedy approach. So we're gonna do np.random.choice, right? So we're gonna do a random.choice between, so we're gonna have our greedy action, right? Plus none. So I'm writing it this way so that we know that the greedy action is always the first here. And then we're gonna say, we're gonna put a probability for our random.choice, and the probability itself should be probability of greedy action plus probability of explorative action for I in range. So for I in range, the length of our non-greedy actions. And we are going to return the action and action value dict action. So we're going to return the action and its value. So with this, we have implemented. So this is using an epsilon greedy policy. Right, that's how we're selecting our action here. So we go back to train. Let's try this again. Okay, it gives us actions and their values. So sometimes it selects, let's see, yes. So sometimes it selects the greedy action, maybe other times it selects just some random action based on the value for epsilon. So that's the idea here. So now that we have this going, so we initialize our initial state, initial action. So we are in this part of the algorithm essentially, where we're initializing these things. And then we're going to need to take action A, and then we need to observe reward and our next state, right? That's the next part of the code. So what we need to do here, we need to take this action, right? And then move on to the next part of the code. So I'm just going to define a couple of things before we do that. So we're going to set episodes is equals to 0 because we're going to be iterating for a number of episodes. And should I define steps? No, that's fine. And let's define, let's say, total reward that we accumulate through this. So while episodes, because we're looping for each episode again, in the pseudocode we're supposed to loop for each episode, and we're on this line here, like take action A. That's the line we're supposed to implement next. So all episodes is less than self dot number of episodes, whatever limit we put to ourselves. I think it's 500 in this case. We're gonna define our feature vector, right? So our feature vector is essentially equal to our hash of this feature vector given state and the action. That's what our feature vector is. And then we need to define our next state. Let's say next state reward and terminate it. Here I'm just using like the interface for the gymnasium, like when you take an action, self.environment.step, and you take your action, right? So if you do this, so if you look at our main code here, if we take a step in action, it returns all these items, like the next state, the reward, the terminated, or the terminator is just saying that it is a, how can I call this? Terminated is whether it's a final state, and truncated is whether we actually truncating the episode to be limited to a certain number of steps. That's essentially what this means. So we do this, and then we define our total reward to be plus or equals to whatever our reward is, right? Now, just to follow the pseudocode convention, even though this might not matter much in our case, we have, if it's terminal, we want to update it this way. Otherwise, we want to update it with this function, right? That's the idea here. So if terminated, right? If the state is terminal, in this case, what we want to do is we want to update our weights as, say, reward. And then we have our, say, actually, in this case, we might need to define, we might need to, because self.update weight here, it takes reward, current queue, future queue. Okay, let's define this first. Let's define the update weight function first, so that it's clear. So from here, as we can see in our pseudocode, if it's terminal, we update it as r minus q of s, a, w. But if it's not terminal, we update using this. So we know what our reward is. We know we can find our current q, we can find our future q, But what is the gradient of this? Did we define this? I don't think we did. So let me write this down as well. So essentially, the gradient of Q of S comma A comma W is equal to, so we're taking the gradient with respect to W in this case, so that's just X of S comma A. So the gradient here is just the feature vector itself, right? That's all we're doing. So given this is what we need to do, that means we can implement this part of the function over here. And let's see, where is it? So if it's a terminal state, how do we want to update? Well, we define our W update, our update rule, as being equal to self.alpha times the reward we get, its reward minus current Q, right? So this is just the definition of what's here, reward minus current Q. This is the W update multiplied by alpha. But in this case, our W update is this, longer term. So if it's not terminal, which is else, our W update is equals to self.alpha times reward plus self.gamma, which is our discount function, times our future Q value, right, minus our current Q value, right? So here I just defined what we have, this over here, that's what I'm defining. Okay, this part actually, only this part. That's the part I'm defining. So given this is the case, what we're going to do is, let's see, for the update weight, we're going to say self.w, our weight vector, plus or equals to W update times our feature vector. So we're just going to multiply our W update and our feature vector, and it should be fine. So if we terminate it, let's go back here. If you remember, this is actually our current Q value. Let me put that here. So if terminated, we have our reward. We have essentially our current Q value. We don't have any future Q value in this case. We don't have a future Q value. We have a current Q value, and what else was that? The function, what the parameters? Reward, current Q, future Q, and we have a feature vector essentially. That's the final thing we need to add here. Feature vector, and whether it terminated, this is true, right? Okay, it's not feature vector here, it's feature vec. Okay, so if we terminate it, we do this. And then we're gonna say state info is equals to self. So because we terminated, we want to reset our state, right? As we will see from the pseudocode, if terminal, we want to go to the next episode. So to go to the next episode, we want to first reset our state, and we want to take the initial action again in the state, self.select action state. So I'm just self.select action state. So I'm just resetting everything again, because this is just our termination criteria. Total reward is 0 again, and number of episodes plus or equals to 1, I guess. So this is basically the logic of terminating, right? So we terminate, we update our weight to the reward, then we update and then we reset our state so that we can start again in the next episode as if we're starting from scratch. So of course there are always like better ways of writing this code, but yeah, I'm just going over like functionality, over like, you know, aesthetics. But if we're not terminating, what we can do is, okay, this, so we're done with this part, right? If S is terminal. Otherwise, we want to choose A as a function of Q. So we want to choose A prime as a function of Q. Then we're going to compute Q of S prime, comma A prime, comma W, right? And we're going to feed this into like our Q function actually in this case. So what this means is we are going to take the next action and find the next Q, which is our future Q in this case, using, so if it was Q learning, we would probably take something like the maximum over all actions, but since we're doing SARSA, we're just going to use our epsilon greedy policy because SARSA is on policy. So we use the same Q to select this action and then self dot update weight. We're going to update our weight. This time we'll update it with the reward, our current Q, our future Q, our feature vector, and epsilon greedy is false here, right? That's the idea. And then we need to do like state is equals to next state, action is equals to next action, and so on. So these are just the final items here. So state is equals to next state, action is equal to next action, and Q is equal to next Q, and so on. And at the end of this one is done, I'm going to just save these parameters as this. Okay, so with this, we're actually done implementing our training algorithm. And I'm just going to add some logging items so that we can see what's happening while we're training. So if episodes, say modulo 50 equals 0, let's print okay, I'm not going to use any string formatting here. I'm just going to try to quickly just, and then we're going to have completed, and our reward is, say, the total reward, whatever the total reward is. So every 50 iterations is going to print this. Oh, sorry about that. So okay, it looks fine. So let me train this. So next action. Okay. So there's an error in our code where we did not define what next action is. Where is that part? This should not be next action. This should be next state. There you go. Okay, as you can see, it is training, and in each iteration it's giving us our average reward. So here, just not to waste time, I'm just training it for a few episodes. And then, given that I've trained this algorithm, next we want to actually make use of it, right? So to make use of the algorithm, like what I'm going to do is say action, instead of taking random actions, because again, let me just show you with random actions, this is what happens, right? But we just trained our algorithm to not take random actions, to do something a bit smarter. And just to be a bit safe here, let me just run it for a few more iterations since I didn't train it for long. But essentially action here, instead of making use of the random, we're going to use the algorithm we just implemented. So we're going to have SARSA.select action state, and we're going to set epsilon greedy to be equal to false in this case. So we're not going to use epsilon greedy, and then we run main.py. We see, okay, it's starting to do something different here. So this is not working fine. Let's see why that is happening. Yep, sorry about that. So for this part, so we are having this error here where we're trying to figure out, Python main.py, and this is not, this wasn't working because I made a mistake here. If not epsilon greedy, was supposed to return greedy action, not just simply return action. So the problem was the select action function. But if we run it now, then we should see that it is working as we would expect it to, right? That's the idea behind this. So we've trained our model, we've trained our weights and everything, and at this point we can say that, well, we can actually make use of this algorithm. We've implemented the final part of it, and that's how we do semi-gradient SARSA. So a challenge for you could be, maybe how would you solve the same problem using, say, Q-learning perhaps. The modification, of course, is not that complicated. I mean, considering that this is just an off-policy algorithm, and maybe you can try to compare the two to also get an idea of when is the best time to use like Q-learning and when is the best time to use something like SARSA in this case. But I'm going to end the lecture here, and in the next lecture maybe we can start talking about deep Q-learning networks. I'll just check, of course, from like the textbook that we're following as well, like if there's anything else we can talk about before then. But that's my plan next lecture. But thank you for your time, and see you next time.